which means that our resistances are actually connected in parallel. R1, R2 and R3. We could also have more, but in this case I am just showing 3. And again we have a battery connected here, and the battery is supplying voltage V and the current moving is I. Okay? So if these were to be replaced with just one R effective, right? If they were to be replaced with just one R effective, we would have V equals, or rather the current. So we know when the current is flowing here, this current is going to split up into 3 different currents. Let's say I1 here, I2 and I3. Okay? I know that I, which is the current flowing in the circuit here, is equal to I1 plus I2 plus I3, right? And in this circuit here, we know that V equals I R effective. Okay? The potential difference, like I mentioned in the previous case, the potential difference across this battery here is the same as the potential difference between these 2 points. So the potential difference between these 2 points is V as well. Okay? So from that we have V equals I1 R1, V equals I2 R2, V equals I3 R3. Okay? So if I have to put, if I have to replace the value of I1, I2 and I3 over here, I would have V over R effective equals V over R1 plus V over R2 plus V over R3. Okay? So we have, I just have to cancel out the V's. I have 1 over R effective equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So this holds true no matter how many resistors I have connected in parallel. Now, so those are the 2 formulas for series and parallel circuits. A few shortcuts or methods that we can use. For example, let's say I have 2 resistances in series, R and R over here. Okay. Now I want to calculate the effective resistance. You should know that if I have equal resistances in series, well, these just add up, right? Okay. Now, in a parallel circuit, a shortcut method to remember is that if I have equal resistances in parallel, the resistance will get divided equally, which means the effective resistance here will be R over 2. Okay? If I have 3 equal resistances in parallel, right? The effective resistance here will be R over 3. Okay? So this is one shortcut that they can use. If you calculate this value according to the formula, you should also find the same result. Now, if I have a current of 6 amperes flowing here, and I have a resistance of 2 ohms here, and a resistance of 5 ohms here, right? Now, I want to know how much current will pass here and how much current will pass here. Okay? So one method would be to actually calculate this, well, by calculating firstly the effective resistance, then calculating how much is the voltage across this, etc., etc., right? Once we have the voltage across this, then we can use that voltage to find what's the current value here and the current value here, right? So that's one way. Another way is to use an analogy. You can think of current flowing in a circuit like I mentioned, like water flowing in tracks, okay? And resistances basically are obstacles. So if this track is blocked more than this track, basically there will be more water flowing here and lesser water flowing here, right? So how much more? It's going to be proportional to the resistances here. So since this is dividing the resistances in a part 2:5, right? So the currents would also be divided in a ratio of 2:5. But only thing is 2 parts would be flowing here and 5 parts would be flowing there. So simple enough, you just add these two, you have 7. 2 parts out of 7 of 6 amperes would be flowing here, okay? And 5 parts out of 7 of 6 amperes should be flowing here. So that should be your answer. You can simply do this. If you have to calculate this using the method that I just told you, you would also find the same result. So this is a shorter and much more intuitive way of understanding this. So yeah, that's another shortcut method that they can be useful for the students. Okay, that's that. Capital resistances. Now, the next portion should be about potential dividers. Okay, first before that, now again, if I have two resistances, which is let's say 2 ohms, okay, and I have a resistance over here of 1000 ohms, okay. Alright, now I can imagine that there is such a big obstacle here that most of the current would definitely flow through here. So if I have I flowing over here, I would have roughly I flowing here as well, okay, and roughly no current flowing through this large resistor, okay. Now, but here's the thing, the potential difference between this resistor would be the same as the potential difference between that resistor, okay. So if I had a way of if this is a device which can measure the potential difference across it, this can be used to measure the potential difference across this portion of the circuit, right? Therefore, this can be a voltmeter, okay? A voltmeter ideally has infinite resistance, okay? But in practically, it has a large resistance, okay? So that a minimal amount of the circuit current actually flows through this, and therefore it's able to accurately measure the voltage across this portion of the circuit, okay? How is it symbolized? You will symbolize a voltmeter like this, okay? And as you can imagine, a voltmeter is always connected in parallel to a circuit. Why? If it is connected in series, it's a huge hindrance to the flow of current, and there's going to be no current flowing through the circuit, okay? So that's a voltmeter. Now, if I have 2 ohms here and I have 0.0001 ohms here, okay? So there's current I flowing through this, alright? And also across this there will be current I flowing, right? Now, there's current I flowing through this, but the voltage across this point, let's say the EMF was V, right? So the voltage across this would still be approximately V, okay? And this one, the voltage across this would approximately be 0 volts, Now, so this kind of a device can accurately measure the current without actually consuming a portion of the voltage of the circuit, right? So this would be how an ammeter works. Okay. Ideally, an ammeter has zero resistance. Okay. Practically, it has very low resistance. Okay. So you have low resistance, and remember that an ammeter is always connected in series, because if you connect an ammeter in parallel, when the current has a choice to flow either through 2 ohms or through almost 0 ohms, the current would obviously flow all through 0 ohms, and that would mean that that's a short circuit. You would have all the current flowing through the ammeter. So you don't want that to happen as well. So ammeters therefore are always connected in series. How do you symbolize an ammeter? Ammeter has this symbol. So that's how you use a voltmeter and an ammeter. Next portion is about potential dividers. So if I have an EMF of V over here, I have a resistance R1 over here and a resistance R2 over here, right? So let's say the potential difference across R2 is V2 and the potential difference across R1 is V1. Okay, so what would be the values of V1 and V2 in relation to V? Let's see this. Let's say the current is I. Okay, so over here I is equal to V1 over R1, right? I is also equal to V2 over R2. Also, I is equal to V over R1 plus R2. Alright? So, using these, we can see that if you have to see V1 in terms of V and the resistances, V1 would be equal to R1 over R1 plus R2 multiplied with V, right? V2 would be equal to R2 over R1 plus R2 multiplied with V. Okay?